discover on our own, but some mathematician somewhere discovered something pretty neat about long division. And essentially what you guys already know is that if you have a polynomial and you divide out like x minus 5, let's say, if you get a remainder of 0, what does that tell you? That it's a factor, that x minus 5 is a factor, which means what's a root? 5. And if 5 is a root, what's the y coordinate that goes along with it? 0, right? 1, 2, 3, 4, 5. If 5 is a root, the coordinates are 5, 0. So what someone then realized is that if you divide out x minus 5 and you get a remainder of 3, number one, is it a root? No. What's fascinating is that the point 5, 3 then is actually on the graph. Does that make sense? Whatever your remainder is the y coordinate of the x coordinate that you essentially plugged in and checked long division on. So we'll use this in a few different ways. And I'll start with this first section that says determine whether or not each of the following are factors. So rather than doing long division to see if it's a factor, this is just sort of like a shortcut. If they say, is it a factor or is it not? If it's a factor, then when we plug in 2, what should we get? 0. So you would check f of 2. We get 8 plus 4 minus 8 minus 4, which is 0. And if f of 2 gives you 0, that means 2, 0 is a point on the graph. And if, think about that logic, if 2, 0 is a point on the graph, then 2 is a root. And if 2 is a root, is x minus 2 a factor? Yes. In part B, to check whether or not it's a factor, can you still do long division? Absolutely, but it's just going to take you longer, okay? If it says use the remainder theorem, they really just mean plug in what the potential root is going to be. So if x minus 3 were to be a factor, 3 would be the potential root. So plug it in and see if it truly is a root. This one gives us 27 plus 9 minus 12 minus 4, which is 36 minus 12, 24 minus 4, 20. So is 3 a root? No. So then x minus 3 is not a factor. Not only that, but guess what? If we had done long division, what would our remainder have been? 20. So you know how you do long division and sometimes you get down to a remainder of 15 and you have no idea if that's right or wrong, if you made a careless mistake or not? You don't really know. Now you can find out what your remainder was supposed to be. So if you're dividing out an x minus 3, you could plug in a 3 to see, okay, I'm supposed to be getting a remainder of 20, and then you're checking your work, essentially. Because if you got a remainder of 20, it would be highly unlikely that you did something wrong. And then on the last one, what number should I plug in and check, Owen? Nope. If x plus 1 is the factor I'm checking, negative 1 is what I'm plugging in to check. And that gives me 0. So that one is a factor. So now that we've actually done it, I'll go back up to this notational description. If f of n equals 0, then when the function is divided by x minus n, there will be no remainder. Does that make sense? You could say a gazillion things from this. You could say that x minus n, if f of n equals 0, then x minus n is a factor. You could say that n is a root. And that's really what this section says. If f of n is 0, then n is a root. If n is a root, then x minus n is a factor. And if x minus n is a factor, then f of x divided by x minus n will have no remainder. Hence the reason why whatever you get when you plug it in, that's the remainder. It's just an arbitrary number that you might plug in. So f of 3, then 3 is a root. If 3 is a root, then x minus 3 is a factor. Like, it's just a generic variable to stand for any number. Yeah. Okay. We don't really need to worry about that description just yet. It's sometimes the way that they have to explain it using math notation makes it more complicated than it is, so I'm just going to bypass that. And then go to this one. If this ratio was placed in this form, essentially, if you were to do the long division and you get the quotient plus the remainder over the x minus 9 divisor, where q of x is a linear function, then which of the following is the value of r? So you could do long division out and see what the value of r is, or what could you just plug in? 9. So if I plug in 9, 9 squared minus 11 times 9 plus 22, whatever I get is what my remainder should be. 81 minus 99 plus 22, 4. If we were to take the time and do out the long division, we would get a remainder of 4. Which means 9, 4 is on the graph, number 1. Which means 9 is not a root then, obviously, if we got a remainder. Because the only way something's going to be a root is if the y-coordinate is 0. Any questions? Look at exercise 5. Exercise 4 is just a lot of the same. To check if x minus 3 is a factor, we're going to plug in 3. To check if x plus 1 is a factor, we're going to plug in negative 1. We're going to plug in negative 5. We're going to plug in positive 5. We just did all that in the front, so we're good with that. 5 is a little bit different, more thought-provoking, and again, a type of question that I might never think to ask on this topic, but the way that they phrase it is very Common Core, making you think on your feet. And you will get stuff like this on your Regents that I've never seen a problem exactly like this before, but we have to think about the concepts that we know. So for what value of k will x minus 4 be a factor of this? So we want x minus 4 to be a factor. So in other words, when we plug in what, we want it to equal 0. Right. If you want x minus 4 to be a factor, then when you plug in 4, we want this to equal 0. So plug in 4. We want it to equal 0. That's the remainder theorem at work. And it allows us to solve for k. If x minus 4 is going to be a factor, 4 has to plug in and give us 0. So we get 16 plus 4k minus 52. Add your 52 over. Subtract your 16 over. We get 4k equals 36. So what is k? 9. And what I would recommend, graph that function and make sure x minus 4 is a factor. So x squared, if k is 9, that'll be plus 9x minus 52. And there we have 4 is a root. So does that make sense that x minus 4 is your factor? Yes. Okay. And then 20 down here was also a very interesting multiple choice that we saw on one of the regions is that I never would have thought to throw a graph in this concept. But they tell you that the graph of a quadratic is shown. What is the remainder when f of x is divided by x minus 2? So if f of x is divided by x minus 2, what would we plug in? What did you say, Bella? 2. So we essentially need to look at the graph and see what that y coordinate is that pairs with 2. What is it, Angie? 2 what? The point on the graph is 2, comma, negative 5. So, what's the remainder? Negative 5. Does that make sense? That should be requiring very little work. I will tell you, I have had people see a question like this and try to write the equation of the parabola first. So they would like take the vertex, they would write, they know that HK is 1, negative 6. They'd take another point, xy, let's say 2, negative 5. They would plug it in to solve for A, and then once they had A, they would have the equation of the line, and then they would actually do the long division and divide out x minus 2, which is genius, really. It tells me that they really understand, but that they weren't sure how to use the shortcut, which I would get if they'd never seen something like this before, because the first time this came on the Regents, not one of the Algebra 2 teachers had ever asked a remainder theorem question using a graph. But if you want to see if x minus 2 is a factor or what the remainder is going to be, you know that you would plug in 2 to the function if you had it, but you don't have the actual algebraic function, you have the visual function. So you still kind of plug in 2 and see what you get, and that right there is your remainder. Good?